All right, so we're really getting close to the end, and the most of chapter 4, the sections are kind of interchangeable. It's like you don't really have to do them in a specific order. They all kind of connect a little bit, but then they're all a little bit disjoint. The chapter doesn't build completely, so this section actually was titled section 4.7. I decided to make it 4.6 just because 4.7, it's probably better to have it after this section. So in this section, there's a lot of review of an earlier section when we did the counting principle, essentially when we made lines, put numbers above the lines and multiplied them to figure out how many different ways experiments can be done successively. And so we'll relive that, and then we'll introduce something called a permutation. And a permutation is a permutation problem is a special kind of counting principle problem that can be solved using a formula. And I'll bring up the concept just because it's a word that you probably are familiar with. I know right now the NFL football is getting ready for their playoffs, and you'll hear announcers talking about the number of different permutations of how the playoff seedings might work out. You'll hear the word permutations, and so it might be nice to be at least a little familiar with what mathematically permutations mean. Sometimes when people use the word permutations, they use it incorrectly. So we'll talk about it. Quite honestly, because permutations are a special kind of counting principle problem, the problems that we can use permutations to solve, we can also use the counting principle. And I'm kind of the opinion that learning one way to solve a problem and getting really good at one way is probably better than learning multiple ways, especially when the multiple ways only work for a very specialized group of problems. So I'm going to really gloss over the permutation problems because the problems that are in this section, permutation problems, can be solved using the counting principle for the most part. There's one group of problems right at the end of this section that we'll get to, and they only can be solved one way, and the counting principle won't work. So anyways, the counting principle is something we did, I forget exactly what section it was now. Doing so many lectures this break that the sections are starting to run together. But right at the front of that section, we said the counting principle is if a first experiment can be performed m ways, and a second experiment can be performed n ways, then the two experiments done in that order, m by n, can be performed m times n ways. And then the next three examples I'm going to do are completely counting principle problems. I said here when I wrote this, they might be a little more involved than what we did earlier in the section, but I don't think they are. I think we did problems just like these, so this is going to serve as a review as much as anything, and then I'll make the connection between the counting principles and permutations, and say that I probably wouldn't learn how to use the permutation strategy to solve problems because it's just too specialized. So, example, a computer password is to consist of 2 lowercase letters followed by 4 digits. How many passwords are possible if? So this is an experiment problem. My experiment is picking a letter for the first letter in the password, a letter for the second letter in the password, and then 4 numbers, and I'm going to call them digits because digits imply just the numbers 0 through 9 are acceptable. If I said numbers, then maybe we can have a lot more choices. So my password is going to be letter 1, letter 2, and then number 1, number 2, number 3, number 4. And when we say digits, only the numbers 0 through 9 are allowed. So this is my 6 experiments, picking letter 1, letter 2, followed by the 4 digits. So because this is doing 6 consecutive experiments, the counting principle says if I just tell me the number of ways each experiment can be performed separately, if I multiply all those numbers together, I'll get the total number of ways this task can be completed. So what I'm going to do is set up for my multiplication, for my counting principle. I'm going to make 6 slots, 1 2 for the first letters and 4 for the digits, and I'm going to put time signs between those slots, and above the slots or the little dashes or the lines, I'm going to put the number of choices that I have. And in this particular case, it says I'm allowed to repeat a number and I'm allowed to repeat a letter. So generally there's 26 letters in the alphabet. So if the first letter is W, since repetition is allowed, the second letter can still be that W. So I'm not going to go from 26 down to 25. I'm going to leave my 26 constant. So when repetition is repeated, is allowed, then you're not going to increment down. Similarly, for the digits, there are 10 digits, the numbers 1 through 9. And then again the number 0. That's the 10 digits. And because repetition is permitted, every time I could use any of the digits between 0 and 9, so there's 10 choices every single time. So if I multiply those 6 numbers together, I'll get the number of possible passwords that have 2 lowercase letters followed by 4 digits. Of course, if you're allowed if you're differentiating between upper and lowercase letters, you'd get more, and you can make these problems really complicated really quick. So I'm going to go 26 times 26 times 10 times 10 times 10 times 10, and I get 6,760,000 passwords are possible of the form 2 letters followed by 4 digits. And again, that's assuming that we are allowed to duplicate letters and duplicate numbers. The next little bit of what I'm going to skip over is just my writing up of how this problem works out. And so I don't need to get to that because I already did that. If I take the same criteria, I'm trying to find out how many passwords are possible that have 2 letters followed by 4 numbers, but I change the qualification and say that I can't repeat a number and I can't repeat a letter, then there's going to be less passwords possible because you can't have like a 4431 as a set of numbers or a ZZ for the letters. So I'm going to set up the problem the same way because the passwords in part B of this example are structurally the same. They're 2 letters followed by 4 numbers, but when I go to put my numbers in, I'm going to need to increment down because once I pick a letter, I can't use it again. So for the first letter, there's 26 letters to choose from, but for the second letter, I'm assuming I'm not going to use the letter that I picked first, so there's only 25 letters left. And I'll do the same for the number. For the first number, there's 10 digits to choose from. Once I pick a number, I can't choose it again, so there'll be 9 for the second. Once I've picked 2 numbers, I can't use those again. There's going to be 8 for the third and then 7 for the last number. So that's when repetition is allowed, you're not incrementing down each time. When repetition's not allowed, then you're going to increment down. And so if I just do this, 26 times 25 times 10 times 9 times 8 times 7, I get, so almost half as many really, actually less than half as many, 3,276,000 as opposed to the 6 million and something. So just taking that qualification off, you've just made way fewer choices. And then the rest of this is just a write-up of how I got to that answer. We don't need to read that because I said that. And then the part C of this is a little bit trickier. This is probably a little more advanced than what we did earlier in the chapter. So the first letter must be a vowel, and repetition of letters is not permitted. The first digit cannot be a 0, and the repetition of digits is not permitted. So when I go to do my first letter, so my first letter can be any one of, and I'm assuming that A, E, I, O, and U are the vowels. So when I wrote this up for the letters now, I put a vowel first and then some generic letter second. And for the first letter, I only have 5 choices. I don't know which of the letters I picked, but I picked one of the vowels. For the second letter, because it says repetition of letters isn't permitted, I know that I have to remove one letter from the alphabet when I go to pick my second letter. In general, there's 26 letters in the alphabet. I've picked one of the vowels, and for my second letter, that vowel isn't something I'm allowed to use again, but there's still only 25 letters left, and I'm allowed any of the 25 letters. The 21 consonants and the 4 vowels are left. So this letter right there, I don't think I could spell consonants, so 24 consonants, because consonants, that's going to be ridiculous. And hold it, idiot. There are 21 consonants and 5 vowels, and what's left to pick for my second letter is 21 consonants and 4 vowels, so there's 25 letters left. So that's the letter part. For the number part, it says the first digit can't be a 0. So for the first digit, I have the choices of the numbers, the digits, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And I'm going to pick one of those, and that only gives me 9 digits to choose from. When I pick a digit, I can't pick it again for the second one because it says repetition isn't permitted. But for the second letter, or the second digit, I'm allowed to pick 0. So my choices for the second digit are the 0 plus 8 of the 9 digits that weren't used in the first choice. So this is kind of if I picked 4 first, I'd have the numbers 1, 2, 3, 5, 6, 7, 8, 9, and 0 left. There'd be 9 digits left. And then I don't know which one of those I'm going to pick, but I'm going to pick one of them. And then when I pick one of them, I'm not allowed to use it again. So there's going to be 8 digits left. And then for the last one, there's going to be 7 digits left. So it's quite a bit trickier when you are putting specific restrictions on individual places. So hopefully that worked out okay. We'll do more of these if that one example wasn't enough to have you, be a kind of pro at it. So let me do this. 5 times 25 times 9 times 9 times 8 times 7. And you get, and you get 567,000. So that's quite a bit less than the 6 million that we started with and the 3 million that we came up with in the second situation. Again, the rest of this is just a write-up explaining that, how I get to the 567,000. All right, so next example, Bob, Sue, Larry, Sally, and Fred. So Bob, Sue, Larry, oh gosh, I have another S, so Sally and Fred. There's 5 people waiting in line to buy concert tickets. How many different ways can they stand in line? Well, there's going to be a first, second, third, fourth, and fifth person. So I made a line for who's going to be standing first in line, who's going to be second, third, fourth, and fifth. And it's kind of it's a counting principle problem. An experiment, the first experiment is picking the first person in line, and then the second experiment is picking the second person, and so forth. The first choice, I'm going to pick one of these 5 people and they're going to stand in line. It doesn't say it specifically, but this is like a repetition is not allowed problem, because once a person is standing in line, a person can't be like both first and second or both first and fourth. So let's say that Sue was first. For the second person, there's only going to be 4 people left. Let's say Sally was second. For the third person, 2 people are already standing in line, so there's only 3 people left. And when I go to pick the fourth person, 3 people are already standing in line, there's only 2 people left. And then when I go to pick the last person, there's only 1 person left. So that's 5 times 4 times 3 times 2 times 1, and that apparently comes out to 120. 5 times 4 is 20, 60, 120. Let me make sure I haven't fudged that. So 5 times 4 times 3 times 2 times 1, and that is 120. So like down here I said this is even though it doesn't say repetition is not allowed, it's assumed by just the physical nature of the problem. if repetition was allowed, it would mean the same person could be in two places in the line at once, and that's not possible. So part B is where things get a little bit harder than the last section that we did this. So how many ways can they line up? Again, the 5 people are Bob, Sue, Larry, Sally, and Fred. And so how many ways can they line up if Larry insists on being in the middle? Well, if Larry insists on being in the middle, that changes things up quite a bit in terms of how the order that I place the numbers in and which numbers I put in. So I made my 5 spots, and I made a spot for Larry. And Larry has to line up in the middle, so there's only one choice for the middle person. It has to be Larry. So I'm going to remove Larry from my list of 5 people because I placed him. And then after I place Larry, I'm going to place the first person, the second person. I've placed Larry, he's third. I'm going to replace the 4th and the 5th person. So now I go to pick the first person. Larry can't be first because he's already picked the middle spot. So there's 4 people to pick from for the middle spot, for the first spot. So I'm going to put a 4 for the first person. It doesn't matter which of the 4 people line up first. They can't line up again. Once I pick a person for first, I've got the first person and I've got Larry in the middle. There's only going to be 3 people for the second. And then once I pick a second person, I have a first person, a second person, a third person. There's 2 people left for the 4th position. And then once I pick a 4th person, there's 1 person left for the last position. So it's going to be 4 times 3 times 1 times 2 times 1. 4 times 3 is 12 times 2 is 24. This should get 24. Okay, so again, I need to know these people. I don't remember their names, idiot. So there's Bob, Sue, Larry, Sally, and Fred. And in part C, it says Sue insists on being first. So in the first of my 5 dashes, I'm going to make a spot for Sue, and she goes first. And Bob insists on being last, so in the last position of my 5, I'm going to place Bob. I'm going to remove Sue and Bob for my list because they're already placed. And now I have to place the second person, the third person, and the 4th person. And I'll just go in order. When I go to pick the second person, there's only 3 people. Larry, Sally, and Fred are the only 3 people that can be the second person. So there's 3 choices for that. And it doesn't matter which of the 3 people happen to go second. Once you pick one of them, there's only 2 persons left for the 3rd position. And once you pick one of the 2 that were left, there's only 1 person left for the 4th position. So it's going to be 1 times 3 times 2 times 1 times 1, and I can do that. That comes out to be 6. So for me, these problems aren't particularly hard, but I've done a lot of them. So hopefully after seeing 3 of these problems that have a little twist to them, they don't seem that overwhelming, but we'll get these in the homework, so you'll get to experience them again. So now I'll talk a little bit about the new word permutations. And you could, if you don't want to get bogged down with stuff that really isn't necessary, you could skip trying to figure out how far we can skip. You could skip to here. So this is where we start again. I'm going to do 3 examples introducing the concept of permutation. And like I said, a permutation is a specialized counting principle problem that gives us the ability to solve problems with a formula. And like I said, I I personally never use the permutation formula to solve problems that can be solved by the counting principle, because they're specialized problems. There's going to be something that I mention in the as I'm doing this that's going to be moderately important, and this is the concept of factorial. Something like, if I saw a 5 with a factorial symbol, 5 factorial means 5 times 4 times 3 times 2 times 1. And my calculator knows how to do factorials. So to do 5 factorial on my calculator, I type the number 5. I hit the math key. I arrow over to PRB because it's a probability thing. And I go down to the exclamation point. And there's 5 factorial. Not that I barely could see that. So in 5 factorial is going to be 5 times 4 times 3 times 2 times 1, which is 120. If I did 4 factorial, 4 factorial is going to be 4 times 3 times 2 times 1. So 4, and then math, PRB, down to factorial. There's 4 factorial, that's 24. 3 factorial is going to be 3 times 2 times 1, that's going to be 6. On my calculator, I'd go 3, math, PRB, factorial. Well, if I could actually press that, 3, math, PRB, factorial, and that's 6. 2 factorial is 2 times 1, which is 1. 1 factorial is just 1. We'll actually need 0 factorial from time to time. So 0, math, PRB, factorial. And 0 factorial is defined as 1. And I'm not sure why, but I know that it works. Let me just do, I might need 6 factorial at some point. Six factorial is 720. You'll probably want to have this sheet handy, and I'll just duplicate this sheet for myself. Some common factorials. It'll be nice when we get to the last group of problems in this section to have these at our fingertips. It'll make some work easier. 6 factorial is 720. 5 factorial is 120. 4 factorial is 24, 3 factorial is 6, 2 factorial is 1, 1 factorial is 2 factorial is 2, idiot, wrote that down wrong, and 0 factorial is 1, which is on this sheet, shows that 2 factorial is 2. I might need those, so I'm going to leave those handy, but I won't use them right away. So, getting back to the stuff that you could probably skip out. So if you skipped all the way to here, I don't think it's going to tremendously make this section better by watching what I do now, but it's something I'm supposed to teach, so I'm teaching it just because it's something I'm required to teach, and so I always teach everything I'm required to teach. Even if I don't think it's terribly important. So most of the problems in this section can be solved using the counting principle. That's what we've done so far. The counting principle is where you make lines, you put numbers above the lines, and you multiply them. There's another way to solve some of the problems in this section, and that's using a permutation formula, and it involves using our calculator and a permutation formula. Like I try to emphasize, the permutation formula is trickier to use because you have to know when it is and isn't appropriate. The permutation formula is only usable in very specialized counting principle problems. And by definition, a permutation is just an ordered arrangement of given objects. That's too generic. So as we get into the problems, I'll try to really hammer down what this definition really means. So a permutation is any ordered arrangement of a given set of objects. I'm sure I just stole this definition from Google or some, I don't know, Wikipedia, and it's a correct definition, but it really doesn't highlight what a permutation is mathematically well enough to be able to use it to solve problems. There's a formula that involves permutations, and it has factorials. That's why I brought up the factorials to start. So this formula says if we're making a permutation of R of n distinct objects, they obey the formula n factorial over n minus r factorial. Here I said we need to be familiar with factorial, 6 factorial, 6 times 5 all the way down to 1, 3 factorial. So I just talked about some of the factorials because the formula has factorials in it. Not really helping me understand permutations just yet. So a permutation is an ordered arrangement of objects within a set. There's a formula that could help me compute how many permutations there are for a given set. And now I'm going to try to emphasize. So I'm going to do this problem 2 ways. So I have the letters S, T, A, R, and P. They're put on pieces of paper and dumped into a hat. So I have the letter S, T, A, R, and P. And I've put those letters in a hat, and I'm going to remove the one letter at a time, and I'm going to write down the letter, and I want to know how many different ways this can be done. Well, one thing could happen, I could get the letters in this order. Another thing that might happen is I might get a P first, an A second, an R third, a T fourth, and an S fifth. That could happen when I'm picking out one letter at a time and I'm not replacing it. Another thing that might happen is I might get a T, A, R, S, and a P. It may not even form a word. So this problem, what it's saying is that I want to count how many different things can happen when I take these 5 letters, put them in a hat, pull the letters out one at a time, and write down what I get in order. Well, this is completely a counting principle problem. To solve it using the counting principle, I would make 5 dashes, 1 for each of the letters. And now for the first letter, there's all 5 letters available to me. So for the first letter, there's 5 possible letters that it might be. It doesn't matter what it is, but since I'm not replacing the letter in the hat, when I go to pick my second letter, the letter that I've already picked is no longer there. There's only going to be 4 letters to choose from. Once I pick 2 letters and go to pick the third letter, there's only 3 letters to choose from. Once I pick 3 letters, there's only going to be 2 letters in the hat. And once I pick the last, then there's only 1 left for the last. And that's actually 5 factorial. And 5 factorial is 120. So for this problem, there are 120 different ways I can pull these 5 letters out and write the letters that I pick in the order that I pick them. So there isn't any reason to do the problem using any other strategy. However, this is the kind of counting principle problem that is also a permutation problem. For a counting principle problem to be a permutation problem, I have to be making ordered arrangements from one set. So this is a permutation problem because I'm making an ordered arrangement from one set of letters. And so I would say this is a permutation. I'll try to be consistent with how I wrote this up. Of that from the 5 letters, I'm forming groups of 5. So this is completely a permutation problem, and I can do this on my calculator now. So the nice thing about permutations is they can be done on my calculator without using the formula. The permutation formula tells me the way to do this without my calculator, but it's too hard to do it without my calculator, so I'll do it with my calculator. So the permutation formula says, so the permutation formula, P, N, choose R, from a group of N objects, I'm picking R objects, is going to be N factorial over N minus R factorial. And in this particular problem, it's an ordered arrangement of 5 objects. So this is a permutation of 5 objects. A permutation is an ordered arrangement. This would be, formula-wise, it would be 5 factorial over 5 minus 5 factorial. 5 factorial in the numerator is 5 times 4 times 3 times 2 times 1. Would you see that there? In the denominator, I do the parentheses first. 5 minus 5 is 0. And then we have 0 factorial in the denominator, but 0 factorial is equal to 1. So this would be 5 times 4 times 3 times 2 times 1 over 1. And that's just exactly the 120. So the permutation formula is going to lead me to the same math that the counting principle took me to. And the nice thing about the permutation formula is my calculator can do it. To do this on my calculator, I don't have to know what the formula is. I could get from this formula to the answer without writing any other numbers down by just blindly pressing buttons on my calculator. So to do this on my calculator, I type this number 5 first, then I hit the math key, then I arrow over to the PRB, and then I go down to option 2, which is the permutation formula. I hit enter, so now I have the permutation formula in there. It's going to put 5 in for the N, and now I have to tell it to put 5 in for the R, so now I'm going to type 5 again. So what this is telling me is I'm going to use the permutation formula, and the number to the left of the formula is going to go in for the N, so the 5 is going to go in for the N. The number to the right of the formula is going to go in for the R, the 5 is going to go in for the R. And when I hit enter, it gives me the 120. So it gives me a way to avoid the counting principle, but I don't really think it's a great way to avoid it because the counting principle isn't particularly hard to use, and there are times when the permutation formula is not appropriate, and maybe we'll get to those, and I'll try to bring out when it isn't appropriate. So this whole write-up here is how I got the answers using the permutation formula and how I got the answer using the counting principle. Again, if there's one way that will work for a bigger set of problems, I usually teach that way as opposed to the way that's specialized. So next example, same example with the letters S, T, A, R, and P, but this time from my hat, I'm not going to remove all the letters. I'm only going to remove 3 of the letters, and 2 of the letters are going to be left in the hat. Question is, how many different sets of 3 letters could I get? So, one of the things I might get T-A-R. Another thing I might get R-P-T. I might get A-R-S. So this is what this example is telling me. I'm taking the same 5 letters, shoving them into a hat, and I'm only pulling out 3 of them. Question is, how many different groups of 3 letters might I get? Easy enough to do with the counting principle. For the counting principle, I'm going to make 3 dashes. So this is the counting principle way to solve, and this is the way I would generally solve ordering problems. Because it's the best, I think. So I need to pick a first letter, a second letter, and a third letter. Well, in my hat, there are 5 letters to choose from. So for the first letter, there's going to be 5 choices. I don't know which letter I pick, but it doesn't matter. Once I pick a letter, it's not available again because it's not going to be placed back in the hat. For the second letter, there's going to be 4 letters left, and then it's going to be gone from the hat. And for my last and third letter, there's going to be 3 letters to choose. So 5 times 4 times 3. tells me that there's going to be 60 different ways to do this. There are 60 ways to pull out from this hat that has 5 letters, 3 letters one at a time, and write down the letter that I picked out each time in the order that I picked it. This is also can be done as a permutation problem, because it's an ordered arrangement of items from one set. And in this problem, in terms of a permutation problem, I'm picking 3 of the 5 letters. So I'm not picking 5 of the 5 letters. So for the permutation formula, it should be a permutation of 5 letters taken 3 at a time, or in groups of 3. So the permutation formula, when it's an ordered arrangement, it works. To the left of the permutation formula, you write the number of objects that you can choose from. In this case, it's 5. To the right, I pick the number that I'm picking, which is 3. And this, if I'm going to use the permutation formula, I'm going to use my calculator. If I'm going to do, if I'm going to write a string of numbers to be multiplied, I'm going to use the counting principle. So I'm going to use my calculator now. This is what my calculator would do. But I'm going to just do this on my calculator straight out. So I'm going to go 5, math, PRB, NPR, 3. So that's what it's saying is I'm taking, from a group of 5, I'm taking 3 out, 1 at a time, not replacing, and I'm ordering these. And you get the same number, 60. So in some sense, it's nice that you can just bust out your calculator and get your calculator to do that string of multiplication for you. It's really not any easier. And there are times when the permutation problem doesn't work. The permutation problem requires me to be taking everything from one set. Once I'm pulling from different sets, like picking letters for the first 2 and numbers for the last 4, I couldn't do that as a single permutation problem. I'd have to do that kind of problem, the problem that we did earlier here, picking 2 letters followed by 4 numbers. If I wanted to do that problem using the permutation formula, I'd have to do a separate permutation for the letters, and then a separate permutation for the numbers, and multiply them together. And the permutation problem would only work in the problems where duplication is not permitted. So permutations are just too specialized, I think, to be really useful at this level of, at the level that we're at. So all this page just talks me through how I got the answers. One last example, and I'm voting not to do this example. I'm going to move on to something else because it's not gonna increase our ability to do the problems. Here's where we all can meet back up again, because the counting principle has one flaw, and the big flaw of the counting principle, so sometimes the counting principle won't always work. So the counting principle, and the counting principle is essentially making lines and multiplying. And when won't it work? It doesn't work when there's duplicate objects. When there's duplicate objects, it overcounts. And this is what I'm going to try to explain to you right now. So if I take the letters A, and B, and I want to order them, how many different ways are there to order the letters A, and B? And you might try to use the counting principle. The counting principle, how we've been using it, we'd say, well, there's 3 letters to choose from for the first letter, because there's 3 letters, and I don't care which of the 3 letters I pick. Now for the second letter, there's only going to be 2 letters to pick. And for the last letter, there's going to be 1. So applying the counting principle to forming orderings of the letters A, and B, just like forming ordering of the letters S, T, A, R, and P, the counting principle would say that there's 6 ways you can do this. That's not the case. What happens is the counting principle overcounts when there's duplicate objects. And in my list of what I'm ordering here, there's duplicate A's. In the STARP problem, the counting principle worked because all the letters were unique. So I know that the counting principle overcounts this. In fact, I can list this pretty quickly. How many ways are there to order the letters? Here, this is one way. The second way is going to be ABA. That's a different ordering of those letters. And the third way is BAA. I don't think you can possibly list with these three letters another ordering that's different, because I have the B third, the B second, and the B first. The answer to the question, how many ways are there to order the letters A, and B? The answer is actually 3. And the reason the counting principle overstates is the counting principle thinks that the A and the A are different letters, essentially. It's thinking like this is like an ACB. And if it was ACB, then you would get 6. So like if this was asking me how many ways are there to order ACB, it would be ACB, ABC, CAB, CBA, BAC, BCA. So if there were 3 distinct letters, there'd be 6 ways to do these. But the problem is if it's AAB and not, if I change each of the C's back to an A, what the counting principle is doing is it's pretending that that A that are duplicates are 3 distinct letters. And it's counting 6 things when there's really only 3. If you look at this list, you'll start to see, these are the same, these are the same, and these are the same. So we have to be careful when we're making lines and multiplying. We are assuming everything here, they're unique and not having duplication. So the counting principle doesn't work when there's duplicate objects. It overcounts when there's duplicate objects. The nicest way to figure out how many different orderings there are when there's duplication in the objects is using a formula. The formula looks rather impressive, but it's not really that impressive. And this whole sheet here says exactly what I just said. These are the only orderings of these 3 letters. Counting principle is overcounting, so there is no other way to arrange these. To figure out how many orderings there are, probably the formula is the best way. Again, the formula looks impressive, but it's not so impressive. So here's the formula. The formula says n factorial over n1 factorial, blah, 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 through n through r factorial. Not that, I don't have that formula even memorized. So to figure out how many orderings, so the number of orderings how many ways there are to write things in different orders when there are duplicate objects can be accomplished by using a formula. The numerator will have the number, well, we'll do letters in this case, the number of letters, because mostly we're going to use this for letters, the total number of letters, factorial. And the denominator is going to have a factorial for each duplicate letter and how many times it occurs. So the denominator could have as few as 1 factorial if there's only 1 duplicate letter. We could have 10 factorials if there's 10 duplicate letters. So for our problem, we're trying to find out how many ways there are to order A, and B. The numerator is going to have the number of letters factorial. In this case, there's 3 letters, so there's going to be 3 factorial in the numerator. The denominator is going to have a separate factorial for each letter that's duplicated to the number it's duplicated. In our problem, we only have 1 letter that's duplicated, the letter A, So there's only going to be 1 factorial in the denominator, and it's going to be a 2 factorial. So if I do 3 factorial divided by 2 factorial, it's going to give me the number of ways there are to order these. And let me bust that out on my calculator. So turn my calculator on, clear it out, do 3 math PRB down to factorial, and then divided by 2 math over to PRB down to factorial, and I'll get the 3 that I came up with. So there's only 3 ways that are distinguishable that you can tell are different orderings of the letters A, and B. So the next few problems are just learning how to use this formula for the times the counting principle doesn't work. And that talks through that. All right, so now, instead of taking the letters STARP or the letters A, and B and rearranging them, this one wants to know how many different ways can we rewrite the letters from Tallahassee. Well, because there's duplication, so now I don't know how many letters. There are 11 letters in Tallahassee. So I want to rearrange these 11 letters into, different orderings. So, and I can't just make 11 dashes, because if I make 11 dashes, it's going to way overcount because there's duplicate. 1, 2, 3, 4, 5, 6. So I can't use the counting principle. What this problem's asking me is how many different 11 letter arrangements are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How many different 11 letter arrangements are there in the words Tallahassee? And it would be wrong to say there's 11 letters to choose from for the first letter, 10 for the second, 9 for the third, and so forth. That only works when all the letters are distinct. When there's duplicate letters, the counting principle overcounts. So I need to use a formula, and the formula is a fraction. The numerator is the number of letters in the problem factorial. So there's 11 letters in the word Tallahassee. The numerator is going to have 11 factorial. The denominator is going to have a factorial for each of the duplicate letters. The first letter that I see that's duplicated is an A, and there's 3 A's. So the denominator is going to have a 3 factorial for the 3 A's. And then the next letter that I see that's duplicated is the L. There's 2 L's. The denominator is going to have a 2 factorial for the 2 L's. The H isn't duplicated, but the S's are duplicated, so the denominator is going to have a 2 factorial for the 2 S's. And the E's are duplicated. The denominator is going to have a 2 factorial for the 2 E's. So to find out how many different ways there are to order a group of letters when there's duplication in the letters, you form a fraction. The numerator has the total number of letters factorial, and the denominator has a factorial for each letter that's duplicated, the number of times it's duplicated. So this I can do on my calculator. I don't really want to enter this on my calculator because factorials are disasters to do on my calculator. So let me figure out what 11 factorial is pretty quickly. So 11 math PRB factorial. So, oh my gosh. So 11 factorial is 39916,800. And then the denominator is 3 factorial times 2 factorial times 2 factorial times 2 factorial. 3 factorial is 6, 2 factorial is 2. So I can translate this problem into this huge number divided by 6 times 2 times 2 times 2. That's what I'm going to enter on my calculator. I don't care to type that, so I'm going to actually do the 11 factorial. So on my calculator, I'm going to go 11 factorial divided by, put the denominator in a parentheses, and I'm going to go 6 times 2 times 2 times 2, rather than entering the factorials in the denominator. I could have did 3 factorial times 2 factorial times 2 factorial times 2 factorial, but those are common factorials that I know, and so I'm going to change the factorial to what it's equal to before I use my calculator to make my calculator work easier. and that's going to come out to be 831,600 different ways to arrange the letters of distinguishable ways to arrange the letters of Tallahassee. All right, another problem. How many ways can the letter starburst be arranged? Well, let me count how many letters there are there. 1, 2, 3, 4, 5, 6, 7, 8, 9. So in my numerator, there's going to be a 9 factorial because that's the total number of letters. Now I look for duplicates. The first letter S, there's 2 of them, so I need a 2 factorial in the denominator for the 2 S's. The next letter T, there's 2 T's, so I need a 2 factorial in the denominator for the 2 T's. The R, there's not 2 A's, so I don't have to worry about the A's. Now for the R, there are 2 R's, so I need a 2 factorial in the denominator for the 2 R's. There's only 1 B, there's only 1 U, so I've used up all the letters in the word starburst. 9 factorial goes in the numerator for the 9 letters that are in the problem. I get a 2 factorial for the 2 S's, a 2 factorial for the 2 T's, and a 2 factorial for the 2 R's. So this is going to be 9 factorial, and then 2 factorial is equal to 2, so it's divided by 2 times 2 times 2. And I'll just enter that on my calculator, kind of like it looks. So I'll go 9 math PRB factorial divided by parentheses 2 times 2 times 2, and I'll get 45,360 ways you can rewrite the letters of the word starburst. Now we're at our homework. So our homework is going to be, I'm going to do most of the problems using the counting principle until I'm asked to do the how many ways can the word Mississippi be reordered. I won't use permutations unless I'm doing that specialized problem. So, problem number 2, a club has 10 members, and how many different arrangements are there, or how many different ways can they elect a president, a vice president, and a secretary? So this is kind of 3 experiments. The first experiment is going to be picking a president. The second experiment is going to be picking a vice president. And the third experiment is going to be picking a secretary. It doesn't talk about duplication or repetition. I'm going to assume that the same person can't be both the president and the vice president, or the same person can't be both the vice president and the secretary. So I'm going to pick a person for president. There are 10 people in the club. There's 10 people to choose from for president. I'm assuming once the person is chosen for president, they can't be the other 2 jobs. So there's only going to be 9 people left for the vice president position. And once 2 of the club members are picked, there's only 8 for the secretary. I think this comes out to 720. And it does. I'll do your problem real quickly just in case you're not ready to jump into these yet. So the daily double at most racetracks consists of selecting a winning horse in both a first and a second race. The first race has 7 entries, the second has 8. If you want to guarantee winning the daily double, how many tickets do you have to buy? Well, buying 7 tickets for the first race would guarantee you a winner in the first, but your ticket has to have both the first and the second. So you have to have 1 ticket that has the winners of both races. So you have to have 1 ticket that has the one of the 7 horses that wins the first race, and the one of the 8 horses that works in the second race. And so there's 7 possible winners for the second, 7 possible winners for the first, 8 for the second. There's going to be 56 different tickets you'd have to buy, having the 1 horse in the first race and the 4 horse in the second race, or the 1 horse in the first race, the 5 horse in the second race. There's 56 different tickets that you can buy. If you bought all 56, you'd be guaranteed to win the daily double. I would suspect you'd lose money if you did that, probably it wouldn't pay more than $56, and that's small of a race. All right, so our problems for 3 and 4 are essentially the same, except in your problem, you're allowed to repeat using a number. In my problem, I'm not allowed to repeat using a number. So we have a locker combination for both of us in problems 3 and 4, and has 3 numbers. So I'm going to pick my first number, my second number, and then my third number. There's actually 25 numbers. The numbers 1 through 24 and then 0 give me 25 numbers. So for my first choice as well as your first choice in problem 3, there's 25 different numbers that are permissible. For you, because repetition is allowed, you can use 25 every time because you can use the same number again. For my choice, repetition is not allowed. So for my second number, there's only going to be 24 to choose from, and my third number, there's going to be 23 to choose from. For you, it's going to be 25 times 25 times 25 because you're allowed to repeat numbers. But I have to increment down once each time because I'm not allowed to increment numbers. And for my problem 4, it's going to be 13,800. For yours, it's going to be 25 times 25 times 25. 15,625 would be the answer to number 3. Ugh. So again, our problems are similar. Your number 5, repetition's not permitted, so you're going to increment down. Mine, repetition is permitted, so I'm not going to increment down. So Social Security numbers are 9 digits long, so we have a first, a second, a third, fourth, all the way to a 9th. So I'm placing 9 numbers for my Social Security number. Mine might blow up my calculator. So in reality, repetitions of digits is permitted. I don't know if anybody has a Social Security number that has all zeros or all ones, but maybe somebody does. In my scenario, repetition of digits is permitted, and there are 10 digits to choose from, the numbers 1 through 9 and then 0. So when we say digits, we're assuming we're only allowing 1-digit numbers, and there's 10 of them. And for me, every single choice for a number is going to be, there's going to be 10 choices because there's 10 digits and I'm allowed to repeat using my digits. For you, you're going to have to increment down because repetition isn't permitted. I think mine's going to be a 1 followed by 9 zeros. So it's going to be 1 billion. Let me try that. 10 times itself 9 times. 2, 3, 4, 5, 6, 7, 8. I think I have 9. Oh, it tells me I'm an idiot. 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Just delete that. And I get that 1, and then there's 3, 6, 9 zeros. Yours is quite a bit smaller for a number, and it won't be easier to write because it won't have all those zeros to track down. These we did earlier in the chapter. So Anthony was making it, for me, Anthony's making an outfit with a shirt and a tie. He has 6 shirts and 4 ties. You can get 24 outfits. For you, you're going to make 2 little dashes, one for the stone, one for the metal. Multiply away and you'll get your answer. Your problem 9 is just like the ring problem. It's just like Anthony's shirt problem. Mine, I'm doing a batting order. We have 9 people on a baseball team. Someone's going to bat first all the way to 9th. So I need to figure out how many batting orders are possible. Running out of room here. Really running out of room here. So 9 people are playing for or starting for a baseball team, I need to make a batting order. If there's no restrictions whatsoever, there's 9 people that can bat first. The person, once somebody's batted, they can't bat again in the order until their spot comes around again. So I need to increment down 1 each time. There's going to be 1 fewer person to bat in each subsequent position. That's actually 9 factorial. I'm going to do that on my calculator and be slick. I'm going to go 9 math factorial rather than doing 9 times 8 rather than going 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Get exactly the same answer. So for my problem 10, there's 362,880 ways batting orders that are possible. Imagine your answer was 12. Oh, okay. Oh, so your batting order problem is the pitcher must bat last. My batting order problem is if a specific person must hit 4th. So there are 9 people. So there's a first, try to write smaller this time, second, third, 4th, 5th, 6th, 7th. Problems don't feel that annoying when I write them up, but now it is annoying. So for my problem, there's a specific person must hit 4th, so there's only 1 player to choose from for the 4th player. Now there aren't any other restrictions of the other 9 starters, so any of the other 8 people could bat first. And once I place a first, I have 2 of the 9 picked. I'm going to increment down 1 to each time because I can't have a person bat more than once and everybody needs to bat. So the reason I'm going down at each time I place one, because I have 1 fewer person to pick from. That's actually 8 factorial, but I'll just do this. And I won't use the 1, so I'm going to go 8 times 7 times 6 times 5 times 4 times 3 times 2. And you get 40,320. I think you'll get the same answer for yours. Hopefully this lecture is going well. I'm doing so many lectures this Christmas vacations. Like I'm doing 1 or 2 every day, and I'm doing a little bit of prep work before I do my lecture, and then a little bit of reflection afterwards. And it's like gobbling up my whole vacation. And I feel like some of the lectures I'm kind of maybe going through the motions more than being passionate about my lecture. So please, if there's any lecture that's just, if you can't learn from a lecture, let me know, and I'll reshoot it when don't feel so rushed. But I feel that I need to get this done before school starts, and so I'm coming to school every day, like even on Christmas Day I came, and trying to get this done so I have something for a class. Otherwise I kind of have to use the class that I've been using. And I wasn't that excited about my class, so I'm trying to improve it. So, you have another batting order problem, and your first 4 batters are already assigned, so in your first 4 positions, there's only 1 choice. And then your last 5 positions, the 5 batters that are left can go in any order. Multiple choice test has 5 questions. Each has 4 choices. How many ways are there to answer? So there's a first question, a second, a third, a fourth, and a fifth. So my goal is to figure out, if I'm just going to guess, how many ways can I guess? Well, it doesn't say anything about repetition allowed or repetition not allowed. I'm assuming that, like, if the choices are A, B, C, and D, that I can guess all A's or 2 A's and 2 B's, that I'm allowed to guess the same letter over and over. So this is like a repetition is allowed problem. Even though it doesn't say it, I infer it just based on the reality of this problem. So for the first question, I can pick any one of the 4 choices, And regardless if I picked A first, I can still pick any one of the 4 choices every single time. I'm not going to increment down 1, because that would be like saying I pick A here, I can't pick A again, now I can only pick from B, C, and D. If I pick A and B, now I can only pick from C and D, and that's not the case. Each question is independent, and I have 4 choices for each, so I'm just going to multiply 4 times itself 5 times. And I get 1,024. So these are really repetitive of what we did earlier in the chapter, so hopefully you're getting really good at these. Oh. All right. So 15 and 16 are kind of brother problems. On 15, we have the same multiple choice test. On 15, you know the answer to the first question. On 16, I know the answers to the first 2 questions. So I'm going to have, question 1, question 2, question 3, question 4, and question 5. And for my first 2 questions, I know the answer, so there's only one guess I can possibly make, which is the right answer. So I'm only going to have 1 choice for my answer for problem 1, unless I want to get it wrong, and 1 choice for problem 2, because I want to pick the right answer. And for the next ones, I'm just going to know nothing and randomly guess. There's 4 choices for each one of those. Because I don't know the answer and I didn't say anything about, I can narrow it down. So for each of the last 3, I'm just going to guess one of the 4 choices. And that's going to give me 64 possible choices. Oh. 17 through 20, identification code has 2 letters, letter, followed by 4 digits. How many different codes are possible? Your problem 17, repetition is permitted, so you're not going to increment down. There's 26 letters and 10 digits. For my problem 18, so I need first letter, second letter, first digit, second digit, third digit, and 4th digit. The first letter must be A, B, C, or D. So for the first letter, I'm going to pick 4. Repetition isn't permitted, so initially there's 26 letters in the alphabet. I pick one of them to go first, one of those 4. There's going to be 25 letters for my second letter. Whichever one of the 4 letters wasn't picked, isn't available again, and I have 25 left. And then my digits, I'm going to increment down. There's 10 digits for the first. I pick one. I can't use it again. I go 9, 8, and 7. On your problem, because repetition of both letters and digits is permitted, you're going to have a couple of 26s for the letters and 4 4s for the digits. So 4 times 25 times 10 times 9 times 8 times 7. I get 504,000 for my problem 18. 19 and 20. So for your 19, again, we're doing 2 letters followed by 4 digits. So it's letter, letter, digit, 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 digit. Mine's repetition for either is the only thing that's not permitted. I don't have specific letters that are required in specific spots. So my first letter is 26, then 25, and then 10, 9, 8, and 7 for no repetition on the digits. For yours, your repetitions of numbers is permitted, so your digit part is going to be straight 10s. Your letters is going to increment down because you're not allowed to do those. So 26 times 25 times 10 times 9 times 8 times 7, and I get 3,276,000 for my problem 20. License plates have 3 digits by 2 uppercase letters, so I'm going to get a digit, which any number from 0 through 9, a digit, and a digit. And then uppercase letters, doesn't really matter that they're uppercase, unless I was allowed to have both uppercase and lowercase, then it would matter. So I sketched out my license plate, and now I'm going to figure out how many of each number and how many of each letter is possible. Because repetition is permitted for both of them, I'm not going to increment down. On yours, neither are allowed to have repetition, so you're going to increment down. So I'm going to have 10 digits for each of the number parts, because I'm allowed to repeat both letters and numbers. And I'm going to have 26 numbers, 26 letters for each of the letter part. You're going to increment down because you're not allowed to repeat either. And for mine, I get 676,000. Seems like I've had that number already. Getting lazy and not putting the time signs between, but they're assumed. So, for 24, the last digit must be even. I'm going to consider 0 an even number, and I think it is. It's a multiple of 2. It's 2 times 0. If 0 is, I teach math, I think I would know. But I don't teach that level of math to get that minutia and know that, but I'm pretty sure 0 is even. So for me, the last digit can be any one of those 5 numbers, so I'm going to put a 5 for the last digit. Repetition's permitted, so I can use, even if I used a 0 here, I could still use it. I could use any one of the 10 digits for the first, and any one of the 10 digits for the last digit, because I'm allowed to repeat numbers. And for letters, I can use any one of the 26 letters twice. So 10 times 5 times 10 times 26 times 26 is 338,000. Yeah, I write these problems, so you think I wouldn't write one that I have a little bit of trepidation about whether something fits or not. So for yours, the first digit can't be a 0, so your first digit can only be 9. And then once you pick that first number, you can't use it again because repetition isn't allowed. So you're only going to have 9 numbers for the second digit and 8 for the third. So these problems can get tricky, I guess. If you haven't done as many of them that I've done, then they might start to sink you pretty quickly. Alright, so these are the distinguishable permutation problems. Here, how many ways can a letter in a word be arranged? I have to use the formula. The numerator is going to be the number of letters in the word. So for Mississippi, there's 11 letters in Mississippi, I think. For Pennsylvania, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I'm going to have 12 factorial in the numerator. And then I'll look for duplicated letters. There's only one P, don't worry about it. There's only one N, E, don't worry about it. But there's a bunch of N's. There's 1, 2, 3 N's. So I'm going to get a 3 factorial in the denominator for the 3 N's. There's only one S, I don't have to worry about it. 1 Y, 1 L, 1 V, but there's 2 A's and 1 I. So mine's going to have a 12 factorial for the 12 letters in Pennsylvania, a 3 factorial for the 3 N's, and a 2 factorial for the 2 A's. And I'd like to know what the denominators are, and I have this sheet here. 3 factorial is 6, 2 factorial is 2. So in my denominator, I'm going to change this to 6 times 2. And I'm going to enter this on my calculator so I don't have to enter so many factorials. So that's 12 factorial. To do 12 factorial, I go 12, hit the math key, go over to PRB, down to factorial, and then divided by parentheses 6 times 2. And for the word Pennsylvania, there's 39,916,800 different ways you could arrange the letters in Pennsylvania and have them look different. For your Mississippi, you could have an 11 factorial divided by what there's 4 factorial for the 4 I's, 4 factorial for the 4 S's, and 2 factorial for the 2 P's. How many ways can these letters be arranged? So in problem 28, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 letters. So the numerator is going to have a 10 factorial. And then the denominator is going to have a 3 factorial for the 3 B's, a 3 factorial for the 3 C's, and a 2 factorial for the 2 D's. So that's 10 factorial over 6 times 2, because 3 factorial is 6 and 2 factorial is 2. So, calculator, 10, math, probability, factorial, divided by parentheses, 6 times 2, and this gives me 50,400 different ways those letters can be rearranged. So your problem's essentially the same. Last one, abracadabra for you, diamondbacks for me. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 letters in Diamondback, so I'll have a 12 factorial. Now I look for duplication. There are 2 D's, so I need a 2 factorial for the 2 D's. There's only 1 I don't worry about it. There are 2 A's, so I need a 2 factorial for the 2 A's. There's 1 M, 1 O, 1 N, 1 B, 1 C, 1 K, 1 S. So the only duplication in Diamondbacks are the 2 D's and the 2 A's. Abracadabra is crazy. In Abracadabra, you have 1, 2, 3, 4, 5 A's. So you're going to need a 5 factorial for the 5 A's. There are 2 B's, you're going to need a 2 factorial for the 2 B's. There are 2 R's, you're going to need a 2 factorial for the 2 R's, and only 1 C and 1 D, and then the numerator is however many letters there are, total factorial. So mine's going to be 12 factorial over 2 times 2, because 2 factorial is 2. So 12 math, probability, factorial, divided by parentheses 2 times 2, and oh my lord, I get that 119,750,400 different ways to rearrange the letters of Diamondbacks and have them look different. So that's the whole section. Hopefully this lecture wasn't god-awful and you got something out of it. If not, again, let me know, and I will take the time to lecture better, because when I'm not as kind of burned out as I am right now, I probably can do better on most of these.